Okay, so 30, we're going to start with 33, and the question which was asked was, what's the difference?
That's a good question.
What's the difference between 33, it's being pushed to the left versus being pulled to the right? So the big difference is when you draw your force diagram, I don't think we're going to do the whole problem together, but I'll show you the setup. The difference in the setup is now what direction is that force vector if it's being pushed to the left? You know, here the rod is like up here, but you can draw the force vector kind of like this. Does that make sense?
Oh.
Because like, think of this mass, think of it as like a single like point in space. And then think of this line. This kind of takes back to geometry class a little bit. So if the force is being directed this way at this angle, that's the same as saying it's like that. So it has a bit of geometry there. Does that make sense?
Mm-hmm.
Sort of, kinda.
As far as friction force goes.
Well, think about what this is going to do now. So this block is being pushed down. What's that going to increase? Yes, all towards friction. Yeah. So this vector, you can decompose it into its horizontal and its vertical components. Okay. Now, what's the angle on this one? 30 degrees again?
Yeah.
Oh, it's all the same numbers pretty much.
Yeah.
So once again, if this is 100 newtons, this would be, what's the calculation here? Yeah. So yeah, this vector is 100 times the cosine of 30, which is about 86.6. And then this downward vector is, I need to leave some room for the gravity vector. I haven't put that in yet, right? But this vector here is going to be 100 times the sine of 30, which is 50 newtons. But wait, I didn't even draw gravity yet. So gravity, how much gravity is there? 98 newtons. So now, therefore, I tried my best to draw proportionally. How much normal force does there have to be? Yeah, you got to add those up. You got to say that the normal force, this normal force here, must be equal to all the downward force, which is the 50 plus the 98. So there's 148 newtons. The floor is providing 148 newtons of normal force. So then when you do your calculation, so the other difference here is since it's moving to the left, your friction force, since friction is mu kinetic times the normal force, okay? So 0.4 times, now here's the big difference. The normal force is way bigger than it was before. And so therefore, it's going to really affect the calculation here. Cool beans? You have much smaller acceleration. But you're going to notice, as you do this problem, just look back at 32 and notice that there's a lot of similarities. There's one fundamental difference. This one's being pushed into the ground as it moves versus being lifted off the ground a bit as it moves. And that's going to drastically affect the acceleration. Okay? Okay, so then today I'm gonna cover these two pendulum questions, or at least we'll cover one of them. And then we'll cover these weird questions where a mass is hanging off of two ropes, two strings or two cables, and look at the tension. All right. Does that address your question? Does that make sense?
Yeah, thank you.
Thumbs up. Sweet. Okay. Okay. So, maybe some of you guys have not, I'm sure you've all seen a pendulum before, but now I'm thinking I should show a pendulum. Just in case. What is a pendulum? It's just a bunch of string here. This is one enough. Okay. This will be a totally mind-blowing demonstration, I'm sure. Pendulum. What?
Let's use that thing.
I mean, it's just a basic knot. Okay, so pendulum is just like you have a mass hanging off a string usually, and you displace it, and then you let it swing. There you go, that's pendulum. You're not hypnotized. There's some interesting stuff you can do, because if I kind of move my hand sort of at the right frequency, I can get it to keep swinging. We'll cover that later in this class. It's an idea called resonance, where if you kind of impart energy into the system. You all swung on a swing set. It's a tongue twister. Swung on a swing set? Anyway, same idea. You're like basically a pendulum. If you just sit there, eventually the air resistance will sap your energy and you'll just kind of slowly decay down to nothing. But if you kick your legs at the right frequency, you can keep swinging as long as you want. So the question we're going to ask is, if you take a pendulum and you know the length of the pendulum, in this case it's 2 meters, so pretty big pendulum, and then you displace it by some angle. In this case, it was, did they give us the angle? 35. So say you pull it 35 degrees away from equilibrium. Right as you release it, what's the acceleration and what's the tension? That's the question. Okay. So just looking at it, you can see that the acceleration is not 9.8. Maybe it's not obvious. I mean, it's probably not even close to obvious, but it's not accelerating quite as fast as it would be if it was dropped. So a little bit of geometry here. So let me put the 35 degrees in here. 5 degrees. So here's the beauty of physics. What method do you think we can use to understand a system like this? Do you think I need to invent like a whole new paradigm of thinking about things in order to analyze this? Nope. I'm going to use the exact same paradigm we've been using for everything. It's going to be draw a force diagram, right? Identify the forces, draw the diagram. And this one will involve one little tricky part, but we'll probably see what it is in a second. So what's the first force I might draw on this? We'll get to that. That's a good point. It's going to travel what we call like tangent. So this is a circular path it's going to follow. Does everyone understand why it's a circle?
Mm-hmm.
Yeah. Because there's the radius. It will eventually travel tangentially, but I don't really see anything obvious that's causing a force in that direction, so I'm going to hold off on drawing an arrow. But I do know that Earth is there, right? Earth pulls this thing straight down. Now, because does Earth know that it's a pendulum? No. Earth just sees some mass and goes, your mass, I'm going to pull down on you. That's all I do. I'm Earth. I see mass, pull. Okay. So how many newtons of force does Earth pull down on him with? 49 newtons. Now here's where it gets interesting. This is what Winslow's talking about. Well, this is the direction it's going to move. So just like in the ramp problem, it makes a lot of sense to go, I'm drawing it tangentially here. By the way, that word tangentially means like if you have a circle, tangent to the circle is, you might recall this from geometry or something, but if you're in calculus right now, this is being drilled mercilessly into your head. So you have tangent lines. So this line that, because eventually that's going to change. As the pendulum moves, its velocity vector would be like, does that make sense? So, but in this moment, this snapshot in time, the velocity vector is going to point this way. So that's going to be my x-axis. And where my y-axis will be like that. You may also recall from geometry that a tangent line is perpendicular to the radius. So that's exactly what we have here is this x-axis is perpendicular to my y-axis. That makes sense to everyone? Okay, now, what does that do for us? Well, that raises the question, well, what's the components of my gravity along this direction and along this direction? Do you feel okay about that? Okay. All right, for a bajillion dollars, how big is this angle? $35. Take you back to geometry one more time. It's this idea, two parallel lines. There's my parallel lines. And then you cut it with a transversal. In this case, the transversal is the string. And those angles have to be the same size. Pretty famous result from geometry. That rings a bell, right?
Yes.
Okay. So, so then, trig-wise, how big is this vector here? Well, look at this triangle. So it'd be 49 times. Turn your head sideways. There's the right angle. Does it help if I redraw the triangle? It's like that. This is 49. This is 35. So is this the adjacent side or the opposite side for this angle? It's the adjacent. So which trig function gets used? Cosine. How about this one? This is the opposite side. So it's sine. SOHCAHTOA, right? So the adjacent side is associated with the cosine of the angle. The opposite side. We're sure we're okay with this? Okay.
Yeah.
Been a hot minute.
It's been a hot minute. Okay, so we know then the size of this vector and the size of this vector. So since this vector, let's get numbers for that. So what's 49 times the cosine of 35? Can someone help me out here? 40.1? Thank you. How about this one?
28.1.
Okay. So that means that this vector here is 40.1, and this vector is, oh, I didn't do it backwards. Okay. This is 28.1. We're still okay with this? Okay. And also, guys, make sure you show your work. Make sure this is shown somewhere. You got to show where the sine and the cosine are coming in. Now, this is the hardest question I'll ask so far. What is this number telling me?
What the forces at like moment, because it's not going to change.
It will, yes, as the thing moves, it's going to change. But this, you got it. It's the tension. Because at this moment, this one little moment in time, is the ball moving toward, like, is it going up the string or away from the string? Like, is it moving what we call radially? Is it moving in this direction? The answer is no. Now, this will get more complicated in the future when we start talking about, once it gains some speed, it's going to be greatly complicated because you have to deal with something called centripetal force and centripetal acceleration, which is a pretty interesting thing to think about. But for now, because we're talking about the moment it was released, we can say that this vector must be, at least for the time being, canceled out by that vector. Okay, so the tension in the string must be 40.1 newtons. Okay, before we move on, any questions? No? Okay, sweet. How about, so then what's the net force then?
Would you do graph sheet?
Maybe this will help. Did we not just, we took this vector and we split it up into its two components, right? So do I have to keep looking at this number? Not really, because this vector is the same as this vector plus this vector. So it's redundant to think about them both. So this vector, I've already kind of dealt with them. If I do this, do you guys see what the net force is? Come on, please, it's not hard. It's an easy question, I promise. It's 28.1, right? No?
Oh, yeah.
Okay, so there's, you gotta add up, so guys, for net force, you gotta add up the x-axis forces and the y-axis forces. So in the y-axis direction, how big was this vector again?
40.1.
40.1. So those cancel out. How about in the x-axis direction? It's that, it's 20 to 1.
There's no like friction. Right?
Yeah, there's, exactly. If you wanted to encounter air resistance, sure, you'd have a small little vector there maybe. Although the thing hasn't really started moving yet, we just released it. This is a snapshot just after it's released. So there's really no air resistance anyway, because air resistance depends on how fast you're going. But, okay, so this is the net force. So the net force on the system. Now let's take a second here. Let's phrase this in a physicsy, sciencey way. Where did this net force come from? What's a nice concise way of summarizing where this number came from? We could say it was the tangential component of the gravity vector, of the gravity force vector. So there was a gravity force vector pulling down, and the radial component, okay, the component in the same direction as the string, gave us the tension, so those cancel out, and then the tangential component, right, which came from 49 sine of 35, this gave us the net force, okay? So let's look at the acceleration. What F net equals ma. What's the net force? Very good, 21. The mass, they told us this, I think, right? 5. And so, let's get 5.16. Which is nice. I mean, hopefully we don't get an answer like bigger than 9.8, because obviously that would be wrong. Because if there was no string, it would fall at 9.8. So the string is going to cause the acceleration to be less than that. So, all right. So you guys will some just work time in class tomorrow. Tomorrow's a very short period, so just bring your problem set to work tomorrow. But I'm going to cover 2 more things today. So we'll do
What?
less than 30 minutes.
30-minute class period. Crazy. There's a note.
We're gonna do 38 and like 40, I guess. Maybe we'll do 39, 39 and 40 because we needed maybe more examples of doing it with symbols. Let's do so 39 and 40, and then you can go back and do 37 and 38 on your own. So we'll look at 39. Actually, I changed my mind. Let's do 38. I want to do with numbers. Because the result, it's a very interesting result. Okay? Interesting. So before we do, so this is 38. So before we actually do it, let's ask a simple question. If you hung a 10 kilogram weight off of two vertical strings, what would be the tension in each string? Get it, Kate? Close. 49. Because your equation, well, you had the right idea, that's good. The equation is there's a vector here, tension, there's a vector here, tension. By symmetry, you can assume it's the same. Be very careful of that assumption, though. You can only assume that these are the same size vector because it's a symmetrical system. If you look forward a couple problems, there's plenty of these that are not symmetrical, so you're not going to be able to make that assumption. Makes it a little bit more complicated. But anyway, there's 98 newtons pulling him down. The force equation would be tension plus tension equals 98. And of course, you get 49 newtons. Okay, simple enough, right? Let's take a vote. Who thinks that in this configuration, so in problem 38, if these are both at a 60-degree angle with the ceiling, so this is a 60-degree angle, that's a 60-degree angle, it's still 10 kilograms. Do you guys think each string will have more than 49 newtons, less than 49 newtons, or will it just still be 49 newtons? Who votes for more than 49 newtons? Julia, okay. Henry is considering, and I didn't give you much time to think about it, so just going on intuition. Okay, who thinks it'll be less than 49 newtons? Okay, how about just the same? Huh? To more? Okay. Okay, let's do it. So this is the nice thing about physics. You don't have to use your gut. It's nice to try to intuitively at the answer, but let's analyze it. So how much down force is there on this system? Still 98 newtons. Okay, simple enough. Earth is not aware of the strings or anything. He just sees mass, he exerts force. Now, a little bit of geometry again. Here's an x-axis. How big is that angle? 60. So this tension vector, let's call this what we're solving for. This is T. This is T. What do I really care about? Do I really care about the vertical component of T or the horizontal component of T? Vertical, because I mean, clearly the horizontals, I mean, it's not like they don't matter or anything, but they're just going to cancel out, right? Because the block's not moving left to right. But how big is this vertical component of this vector? How much does this vector tend to push up? T times the sine of 60. Do we feel okay about that? This guy, likewise, is also T times the sine of 60. So what equation can I write t times the sine of 60. There's two of them though, right?
Times 2
Little banana theorem here. 2 times t sine of 60 equals 98. We can use a calculator here, I think. But if you want to be super duper savage, someone make my day here. What is the exact value of the sine of 60? Does anyone know this one?
It's
2.
Close.
Close root 2.
Not less close. The cosine of 60 is 1/2. I'll give you that. Oh man, I failed.
Oh, no.
Yes, root 3 over 2.
Oh, I was doing a 45. That's
Okay, so if you know that the sine of 60 is root 3 over 2, then what happens to these 2's? They cancel out, cancel, and you get a beautiful answer here. You get 98 over root 3. Now a decimal might be nice because it might make the answer a bit more salient. So I don't know, do you think it's obvious? Is that number bigger or smaller than 49?
No.
40, so you do 49 divided,
What's the calculator tell us that is?
56.66.
and then times it by.
Oh, that's the answer. Because we have this embedded in our solution. We have, this is this 2 here, you know what that 2 does? Because the unknown is t, right? Is this force, this magnitude. So when we said that this vertical component plus this vertical component has to equal 98, that's what this equation says. That's what the 2 is doing. It's doubling this vector. This is the tension at each string. So each string has kind of a weird relationship though. It's a bit more tension. It's not double the tension. It's, I don't know, something like, it's not even 50% more tension, but it's different by some factor, okay? You guys feel okay about that? Okay, we're gonna just end it there. Let me know if you, to the millions of fans at home, if you have any questions, let me know. But that's the idea. By the way, it doesn't take, it's not too difficult to imagine what's gonna happen when, say this was 40 degrees, you'd have to set up 2 equations, one balancing out the horizontal components and then one balancing out the vertical components with gravity. You'd have a system of equations, you'd solve it. We'll do that tomorrow or Thursday, I guess. Work day tomorrow.